Hello, everybody. Welcome to this week's reading group session. I know we've not had one in a while, so sorry for the few weeks break, but we'll now be back doing it every week. We're starting to shift the focus a bit to focus on compiler papers as well as compression and a lot of things that relate to optimizing ML models for deployment. There's a lot of really interesting research happening across this kind of area, so I thought we'd kick that off with this really interesting paper from Meta called Large Language Models for Compiler Optimization. Came out a few weeks ago. And yeah, some really surprising, interesting results. It's a relatively simple paper, yeah, nothing that's too fancy architecturally, and really just the long story short is you can apply Llama to 7B unmodified to the task of optimizing LLVM passes, and you can get you can get big speedups over the default flags that LLVM recommends for kind of generic compilations. So basically you can get a model that can get up to 5% improvements over other methods in a very, very naive way. But let's unpack that gradually. So I don't have any slides today, so we'll be kind of just going through the paper as a bit of a backdrop. And then kind of going through the images and everything like this. So high level, to start off with, LLVM is compiler infrastructure, for those that don't know, developed in the early 2000s by Chris Lattner, now ubiquitous across all hardware. It's a vendor agnostic representation. It's an intermediate representation that is part of the progressive lowering when you go from arbitrary code like C or C++ or other languages, and you then express this in this intermediate representation that can then be consumed and used by various vendors. This is a representation that's kind of used by all hardware, and then it can then go down to kind of vendor specific assembly when you then go to the next level below underneath the LLVM representation basically. So being able to optimize LLVM IR code is a huge general problem that really transcends all kinds of programs for all kinds of hardware. So a very fundamental problem that this paper is addressing. So quickly, in their own words, what they say is they explore the novel application of large language models to code optimization. They just use the 7 billion version of Llama 2, and it's trained from scratch. So it's not fine-tuned. It's not trained on the original Llama 2 internet data. It's trained from scratch on a relatively small data set as well, as we'll get to. It takes input the unoptimized code and outputs the optimization passes. So there are a lot of flags, 122 flags that LLVM accepts for doing these optimization passes. It predicts the flags as well as the prediction of the resultant code after these flags have been applied. And also it predicts the instruction count before and the instruction count afterwards. And it says, and they get a 3% improvement in reducing instruction counts over the compiler. And they also outperform state-of-the-art baselines that are also ML-driven, both of which require thousands of compilations. I think one of the interesting points to start with is this, what they say here. Yeah, they say, we thought this would be a paper about the obvious failings of LLMs that would serve as motivation for future clever ideas to overcome those failings. And they were entirely taken by surprise to find that in many cases, a sufficiently trained LLM can not only predict the best optimizations to apply to the input code, but it can also directly perform the optimizations themselves without resorting to the compiler at all. So, and I'll get into that in a moment, but basically, they can actually predict the new LLVM code without needing to actually call the compiler at all, which means that you can literally use the LLM to just do the compilation itself, which is also very interesting. So their approach is simple. Again, they have the 7 billion LLVM, 7 billion parameter LLM, Llama 2, initialize it from scratch, train on millions of examples, and yeah, so relatively straightforward approach. So diving into an image to make this all a bit less abstract, a bit more intuitive. So basically what the process looks like is the following. So they start off with a prompt, which is text-based. It's all incredibly simple. They don't do any special representations here. They just provide as text something that looks like the following. Tell me what passes to run on the following LLVM IR to reduce the instruction count. And then what they train it on are examples like this, which is run passes. You know, these flags here are all part of the 122 optimization passes that you can use when doing these LLVM compilations. And then, you know, so run these passes to reduce the instruction count from X to Y. So they also train the model to know and understand how many instructions were there in the unoptimized original code, how many remain in the optimized code, and they also train the model to predict the code itself after the optimization has been applied. And then during inference, you don't actually need this code or the instruction count. These are actually auxiliary learning tasks that are intended to make the learning easier. And as we'll see later on, they do make the learning easier. But actually at inference, all you need are the passes themselves, because then you can actually use the compiler itself, which generates the optimized code, which in some cases is different. So the actual model, I think, well, we'll see later, I think in kind of 90% of the cases, no, 70% of the cases, the model is that the code is the same. In the rest of the cases, it's not the same, but often the instructions are correct. So yeah, this part of predicting the code and the part of predicting the numbers are just auxiliary training tasks to improve the performance. And then you can actually just take the flags, basically. So that's the overall approach. Maybe just quickly, any questions from anyone in the room at all on that part of things? Yeah, Vasalia?
Yep, so quick question. So the prompts that are generated for LLVM, are those hardware aware? Because a lot of flags, a lot of times don't work on a certain hardware. They usually segfault.
Yeah, so no, it's hardware agnostic. They say that for future work, they're going to actually look at the runtime improvements, but at the moment, it's all hardware agnostic, and they don't actually do any runtime performance. It's all about code size reduction right now.
Right. So right now, the paper doesn't go into too details onto what, like hardware dependencies and different things.
Exactly. They say, I mean, I can actually find it here. They say they do, they mention this. So they target compiler pass ordering. Pass ordering is to select the set of optimizing transformation passes available in the compiler list that will produce the best results for input code. Yeah, it's been shown to have a big impact on runtime performance and code size. Below they talk about previous approaches to this. Yeah, no. So basically they mentioned somewhere, yeah, the approach is, here we go. The approach is agnostic to the chosen compile and optimization metric. We intend to target runtime performance in the future. For now, optimizing for code size simplifies the collection of training data. So right now it's vendor and compiler agnostic. It's just, I guess they assume that whatever passes they do will work on the resulting target hardware. But I guess, yeah.
Yeah, I guess it's just code size reduction at the moment, and I guess they'll get into hardware dependence as well.
Exactly, and they say they leave that to future work. And to be honest, it is the first paper applying a vanilla LLM to this problem. So I guess they just wanted to keep the problem quite simple to start with.
Thanks.
Cool. Any other questions before we keep going through? Kind of high level questions. No question is a silly one. Nope. Okay, cool. So I'll keep going on then. So I mean, I can kind of just quickly jot through kind of the paper just to act as a bit of an anchor. So they present the model with unoptimized LLVM IR, such as that emitted by the Clang front end, and ask it to produce a list of optimization paths that should be applied. Figure 1, we've already had a look at. This just shows the overall approach. They target LLVM 10 and they use the optimization flags from OPT. As I said, there's 122 to choose from here. Yeah, and they also include the 6 meta flags, which can only occur once in the pass list. And these are kind of like higher level flags that kind of combine best practices rather than like doing one particular thing. They're kind of more like do this kind of level of optimization and combine other flags that exist in the set of 122. Yeah, so pass list can be any length, but in their experiments, they found typically up to 9 passes long, which means that the combinatorial search space, assuming that it's up to about 9, is 10 to the power of 18. So a very huge search space because when you do these optimization passes, the order also matters. It's not just the case of like, what are the things, what kind of optimizations do you apply, but the ordering is important. So, you know, ridiculously huge search space to go through. So as I say, they include these two auxiliary training objectives, which is the count of optimization passes before and after, as well as the output IR after they've applied. They hypothesized this would enable better pass orderings, and it does, as we'll see later in some of the graphs. Yeah, and they don't need it for deployment. So again, it's just for training. At the actual inference time, they just take the flags and use the compiler to generate the correct code. And that sidesteps problems from other techniques where the correctness of the model can be a problem. In this case, because there's only these 122 pass orderings, the code will always compile because you just actually run the compiler. What did I say here? So yeah, they normalize the text, so they apply some linting basically to make sure that the code is structured in a simple way. They remove comments and everything, as you would expect in the input and the output as well. So on the model itself, so obviously it's a transformer. It is just Llama 2, and again, nothing too fancy. The input text first tokenized, of course. Embedded in continuous vector representations. Yeah, I mean, again, just kind of very vanilla stuff. The output text is produced by iteratively generating one token at a time. Decoder takes the encoded input along with any previously generated tokens. They greedily sample during decoding to take the most likely token sequence. Yeah, so I mean, it's just kind of Llama 2 applied as you would expect, so nothing to read into too much here. Again, they use the smallest one, so Llama 7B with 32 attention heads, 4,096 hidden dimensions. So it's capped up to 2,048 tokens. That's the context, the sequence length. Yeah, Llama 2 tokenizer has 2.02 characters per token. Yeah, okay, so basically just some architecture details, but nothing that's too interesting really to look into there. They have a training data set of 1 million deduplicated IR functions, which to me seemed quite low. It makes me think that given they've used such a small architecture and relatively small training data set, that yeah, like they might be able to get better performance by scaling this up even more. But nonetheless, so they have yeah, they generate this partly by taking data sets of publicly available C and C++ code, and then they also supplement this with synthetic code generated by C and C++ compiler test generators, making a total of 1 million deduplicated IR functions in the training set, which is, yeah, 373 million training tokens. Again, they operate at the level of individual IR functions rather than entire modules, so they can have more data that can fit inside the sequence length. Interesting, if you extend this to bigger programs, they actually see that as the programs get bigger, there's more and more optimization opportunities beyond the default flags, as we'll get to soon. So I think it'd be quite nice to see this work potentially extending to much longer sequences where the optimization opportunities are much more complex and much more interesting, because I think the search space and the optimal configurations are going to be better. Yeah, so then the way they generate the training data, so this is the question. So how do they generate the ground truth training data for all of this? They effectively employ auto-tuning, where they do this massive search across all of the possible combinations and benchmark them to see which actually do result in code size reduction, and then use that kind of random search as the ground truth for training the large language model. So it combines random search for each function, they run random search for a fixed amount of time, so 780 seconds, so kind of 15 minutes or something roughly, and then minimize the best passes by iteratively removing individual randomly chosen passes. Suffice it to say, rather than going into all the details here, they do a massive search of all of the possible combinations and find the best one by literally assessing the code reduction, and then they use this as a gold standard, which is a very computationally intensive but kind of rigorous ground truth golden standard approach, basically. Again, while the instruction count savings discovered by the autotuner are significant, the computational cost to reach these wins are 9,000 CPU days, so very computationally expensive. And the goal of this work is to achieve some fraction of this performance of the autotuner, but using a single forward pass of a model that doesn't require thousands and thousands of compiler runs, basically. So then, yeah, some training details. Again, I think we kind of want to get into the evaluation. These are all just details you can read about. But yeah, they train now for 30,000 steps on 64 V100. So again, as with all of these transformers, pretty computationally expensive stuff. Trained for 620 GPU days. Again, these Adam with kind of pretty default parameters, cosine learning rate, blah, 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 kind of, relatively, I don't think there's anything too surprising with this. Obviously, everyone's welcome to dive into these details more, but yeah, I won't unpack that too much for now. We can get into the evaluation. Any questions on the way the data is collected and the way the ground truths are generated with the auto tuning, and anything about the kind of setup of what they've done? I've kept it quite high level just because, in the interest of time, we shouldn't unpack every single detail in crazy detail, and there's a lot of evaluation stuff to go through. Any questions for now? Okay, I hope everyone's broadly on the same page. Obviously, if you don't understand every minute detail, that's fine. Also, people, of course, won't necessarily know exactly what the LLVM passes are like. Maybe actually putting you on the spot a little bit, but maybe Vatsalia, would you mind kind of just for a couple of minutes, or like just give a few examples of the kind of things that the LLVM flags do, just for some kind of simple examples?
Yep, sure. So a couple of flags, the major one being -O. What that does is it does order-based optimization in LLVM. So O1 essentially is one instruction of optimization. So it includes fundamental operations like memory sets, data flows, and all these different things. And it's a more contained version of optimizations. Then there is O2, which is a bit more computationally expensive and has more offsets and more optimizations introduced. And just keep in mind that these all optimizations are hand-tailored. So they're defined in a certain way for a certain use case. So a lot of times for certain CPUs, -O2 would do better than -O1, and -O1 would do better than -O2.
Although I'd say these are the meta flags, right? I guess these are kind of the things that you include once and actually combine all kinds of other, like, much more specific. So there's things that are kind of like, I don't know, well, tiling, for example, and also removing for loops and caching the results of those and combining for loops together, and all this kind of stuff.
So a lot of this is actually done when you do -O2. So
no, exactly. But my point was that these O1s are kind of meta flags that kind of combine things together. I more meant some of the actual kind of very specific flags, which are kind of things like, caching computation where it doesn't need to be continually computed, and combining for loops together, and these kind of things, I guess, are pretty common.
Yeah. So there's one called jump skip mem, which basically, essentially what it does is it skips through a lot of registers to save CPU a lot of memory. So essentially what that does is when you get the LLVM IR, it contains a lot less for loops in your assembly code. And this is actually something that I've noticed in this paper as well. They focus a lot on adding a lot of register-based optimizations in the LLVM IR, which is something that I haven't noticed with RL-based approaches, where mostly RL-based approaches would deal with -O3, -O2. This, with the LLM, they've added a lot of register-based optimizations.
Yeah, interesting.
Yep.
Cool. I guess we'll get to all of that in the evaluation as well. But yeah, awesome. Thanks a lot, Vasalia. Cool. Okay. Any other quick questions before we move on? No. Okay. Cool. So now we're going to the evaluation. What is this? Again, pretty simple approach. It's just taking a load of code, running an exhaustive auto tuner to get ground truth, training Llama 2 on it in purely text fashion, and seeing what happens. So again, the fact that it does well is somewhat surprising. So first of all, we can look at figure 2. So you can see, so this is the test set performance. So the auto tuner remains this gold standard. This is the improvement over OZ, which is this like kind of default approach that is this meta flag that combines like best practices and heuristics to get good performance. So this is the improvement in code reduction over this pretty strong baseline. The auto tuner obviously gets a 6%. I say obviously, but the auto tuner gets a 6% improvement with this very computationally expensive approach. Their method, as the training continues, it ends up plateauing around here, getting around a 4% improvement. So not as good as the auto tuner, but again, much less computationally expensive and very impressive nonetheless. This is then the loss for their prediction of the numeric value, this auxiliary loss on the input code length and the output code length. So the input code length is able to predict very quickly, almost 100%. The output code length, it gets to about 90% correctness and then kind of flat lines there. So it's not always able to fully understand how many code passes are in the returned code after optimization passes that are applied. Obviously, that's a much harder task than getting the input where you have the ground truth code actually there to analyze. And then this is then the returned code. Again, this is the auxiliary loss. So the code that is outputted by the model in about 60% of the time, it's an exact match, character for character match to the true code that results from applying the compilation flags that are returned. In about 80% of cases, the code is able to compile. So the code is semantically correct and without errors. And this BLEU is some kind of, some evaluation metric that compares the similarity to the generated code and the resulting code based on some kind of string comparisons. I don't exactly know how it works. They've not explained it, but they say that when you take the original code and the compiled code, it would have about a 0.5 score. So it's obviously able to get close-ish to the ideal code, basically. So just showing that the auxiliary loss, it improves on both of these auxiliary losses, it improves over time. We then have the results here. So they show compared to some baselines. Just for the interest of time, I won't go into lots of detail on what these two are, but suffice it to say that I think autophase is the RL approach, Corset is a graph neural network approach. Both of them involve compilations. It's kind of these iterative tree-based approaches that actually try to encode a loss function on how good a certain set of passes is. So given these passes, how good should this code look like? And then you can kind of search the kind of, you can search the space of all possible passes and do some kind of iterative RL-driven search through that space. So they include a lot of compilations as part of the inference step, is the important difference. So their approach obviously has 0. It's just a single forward pass of an LLM. And then we have the number of times that functions are improved over this kind of baseline of the OZ, which is the kind of not the gold standard, but it's like, a very good meta flag that by and large gives good combinations based on the heuristics that the LLVM authors have determined. So yeah, the autotuner, obviously the best, but their approach gets 4,000 versus 3,900 and 1,500. But importantly, there are many regressions for these other two state-of-the-art baselines. In fact, more regressions than improvements, whereas theirs only has regressions 526 times. This is then the instructions saved. So when we do improve it, how many instructions do we save? Again, theirs is more than the two baselines. How many instructions regressed? Theirs is a lot less than the number of instructions that are regressed by the two baselines. And the overall improvement for the autotuner is 5%. Both of the others actually, on average, get worse performance. There's more times that there is a regression over OZ than there is an improvement, whereas theirs has an improvement 3% of the time. Sorry, their average improvement is 3%, whereas the average improvement is making things worse with these two. So then they do another experiment, which is say, well, obviously it's relatively easy to fix this. Let's just say if it's worse than OZ, then we use OZ. So it's not actually getting worse, because there are then still these cases where the function does improve, of course. And when you take this approach, the number of compilations increases a bit, even for the LLM approach, because the idea is, well, if it's worse than OZ, then we use OZ and we do run the compiler to get the result. We do use OZ, so then there are, their approach LLM approach goes from 0 to 5,000. These go up further than they were before, and then we get this. So it's 3.5 overall, increase from 3.01, and then these get 2.55 and 1.02. So they're not regress anymore, but they're not as improved as the new approach. And what's very interesting about this is these other approaches. I mean, I won't go into them into too much detail, but where they talked about evaluation, comparison, state of the art. The interesting thing is that these other approaches are also very quickly, sorry, what they're comparing on are various test data sets, which are, so they take them from coding competitions, compiler test case generators, and miscellaneous publicly available code. So they take various data sets, use these as test sets, deduplicate them, make sure there's nothing in the training data set as well, of course. So this is kind of the baselines. These are the data sets that we're testing on for all of these evaluations. The baseline, so autophase is this RL approach, which uses PPO to select the sequence of optimization passes. CourseNet combines iterative search through all these options with a learned cost model, where you have, given these flags in this code, what do you predict the code reduction will be, and then therefore it's much more iterative, and it also involves compilations during this search. So, but what's interesting is there's a lot more structure in autophase and CourseNet MVP. So they've kind of leveraged the fact that this is a search space problem, and they've done something which is more akin to what kind of Alpha Tensor does, for example, which is to kind of structure the problem and then apply tree-based search. This is what AlphaGo does as well, kind of more this kind of flavor. Tree-based search through the search space using a learned value function to enable you to search efficiently through the space. And the fact that a incredibly brute force LLM approach beats them both, to me, is very surprising and very interesting. Now, yeah, like I'm not sure whether there are things you could do to improve these more structured formulations to the problem, but definitely, yeah, like I guess giving more validity to the idea that you can just apply a big transformer to a problem and it can just kind of work out the structure itself, which is, yeah, very interesting. So that's everything for these graphs. We've looked at the results. It beats the other baselines. Yeah, so the test data sets we just briefly explored. This is the training data. It just says the number of the size on the disk, the number of tokens. I think there's too much interesting there. Yeah, we've gone through these tables. So okay, so then let's just go through a few more of the graphs. So yeah, so this is interesting. So this is their approach versus the auto-tuner. So first of all, actually, in many cases, OZ is the best result, actually, interestingly enough. So this shows, starting from the left, this is the number of times that each of these instructions appears in the optimal pass. So yeah, frequency that passes occur in the pass list for each of the 100,000 test programs, and the length of the pass list on the right. OZ is a starting point for the auto-tuner and is the dominant result. So this is often in the pass list that's optimal. Yeah, so 93% of the auto-tune test programs had OZ included in the pass list. Yeah, the model generated pass list distribution tracks. So the model generated one slightly over predicted OZ. It's not very helpful here because you can't really see the comparison. And it also says the model generated pass distribution includes 9 passes that the auto-tuner used on the training set, but not on the test set. And yeah, results are obviously ordered by decreasing frequency. So I guess one of the main takeaways is that the model follows the distribution relatively closely to the auto-tuner. But then you start to get a few here that are slightly anomalous and slightly outliers. We also see that on average, their model has longer pass lists than the auto-tuner. So it's like over predicting a few. But the fact that you get very strong similarity with the frequency of usage shows that the LLM is learning to replicate the auto-tuner's decisions pretty well. Yeah, which is interesting to see. So getting through to, well, I'll come back again with, are there any questions so far about these evaluation metrics we've looked at so far, about maybe the other baselines they compare against, any of the graphs we've seen so far? Otherwise, I'll keep going. Okay. Well, I'll keep going for now. So let's go through here. So we got the training results. We saw figure 2. We looked at figure 2B and 2C. We've looked at the tables. Yeah, so then comparison to state of the art. We've looked at how it compares to the baselines. We've briefly gone over what the baselines are doing. Okay, so yeah, okay. We've looked at table 3 already. We've gone through table 4 as well. Oh no, we've not gone through. Yeah, we have gone through table 4 as well. So yeah. So, and then figure 3 is yeah, we've gone through this as well. So just showing how that compares to the auto-tuned one. So they mention here broadly tracked. So yeah, so OZ is the most frequently optimal pass, which is interesting. And the actual generated pass lists, when you exclude this, is averaging only length of 4, and the auto-tuner pass have an average length of 3.1. So again, they slightly over-predict the length. And interestingly here, 105 of the pass lists generated by the model, never appearing in the training data. So again, there's indications that it is learning to extrapolate from the data. So the fact that there are cases where the pass list has never been seen in the training data, and yet it still improves the original code, is a good indication that it's not, memorizing training data, which we know neural networks don't do. They do, broadly speaking, intelligent interpolations and extrapolations, and are able to reason with the fundamental logic. But the fact that there are pass lists not in the training data is another indication of this. In 710 of the cases, the model-generated pass list outperformed auto-tuner on the test set. So it's also able to actually beat this kind of very computationally expensive exhaustive search, which is interesting. Listing 1 shows one example where the model did better than the auto-tuner. Although I think unless you understand kind of LLVM IR deeply, it's going to be hard to make much sense of this. But I'd recommend anyone that wants to see an example of the model beating the auto-tuner, then this listing is an example of that. And it reduced it by 1. I think the auto-tune code had 14, whereas the model optimized had 13, and was able to bypass one instruction basically. So yeah, so there's this then. Yeah, so basically what it said, it explains how it improved it. Example where the model generated pass list simplifies control flow to fewer blocks, saving 1 further instruction. So then we have figure 4, which breaks down the improvement of each approach to pass ordering by benchmark datasets. So yeah, basically which datasets are we able to see the biggest improvements? Yeah, okay, I'm not sure there's too much to read into there. There's strong correlation between the input program size and the potential performance improvement. So this is more interesting. So figure 5 plots this. So yeah, there's a strong correlation between the input program size and the potential performance improvement over this kind of meta flag OZ. It's what you might expect. So let's have a look at figure 5. So it's this one in particular that's interesting here. So when the instruction count is larger, there's much more optimization opportunities beyond this meta flag OZ, which is what you might expect, because longer, more compositional programs are obviously just much more complex in this kind of exponentially expanding way. There's more things going on, there's more kind of, let's say, moving parts, and there's more ways that these can be synthesized and fused and combined to do more intelligent things. And the harder it becomes to have heuristics. Obviously, for very simple problems, you can hand engineer heuristics that are always close to optimal. But as things branch out, the search space becomes intractable, and heuristics can only take you so far. And OZ is a heuristic-driven meta flag. So what they see here is that as the instruction count grows, the auto-tuner gets bigger and bigger improvements over this heuristic. Their approach follows, like with each new, with each increase in 10, we get bigger and bigger improvements. So this is indicative of the fact that when you take an entire program, I mean, these are just single functions right now. If you take like, an entire neural network, which would be, tens of thousands of kind of instructions when you combine them all together, you can really imagine that the search space and the optimum combination, is much beyond what OZ can do, for example. So I think that's an interesting trend. And then they do something similar on the data sets, but to be honest, I've not had too much time to go into what these data sets are and what the significance is here. But one thing you can clearly see is that their approach on the auto-tuner consistently gets an improvement, whereas these other benchmarks don't. And for some reason with C-Smith, the other state-of-the-art methods are very, very bad, whereas their approach remains strong. So again, another win for this paper. So then they give a few listings here. I think I'm going to skip over the listings a bit because assuming that because it requires a lot of background knowledge in assembly code and LLVM IR, which I could go into because I've gone through this in some detail and made sense of it, but I think it takes a bit of time to fully explain all that. So I'll bypass that for now. So let's bypass listing 2. So then table 5. Again, they explain the different kinds of errors that emerge in the generated code. So the LLVM IR code that's generated, what are the kinds of mistakes that it makes? So they get a lot of type errors, a lot of instruction forward referenced. But again, having not dived into the LLVM IR myself, I won't dive in. I won't spend too much time on that. So this one is an interesting observation. So they see that the model optimized code quality as a function of performance of the generated pass list. So basically, which is what you might expect, but when the actual code, when the passes that are predicted by the model are not good and it's worse than OZ. So when the model is suggesting flags that cause a regression, the model is very bad at predicting the code that's generated afterwards, as well as the instruction count, and also the code compiles worse. So we have this BLEU, which is a measure of how close the predicted code is to the one that actually comes from the flags that are suggested. So when it suggests these regressive flags, it doesn't really know what the code looks like. When it suggests these regressive flags, the code often doesn't compile that it predicts corresponding to the flags, and also it doesn't know how many counts it doesn't know how many instructions the code actually will have. So it kind of just shows that when it's making mistakes, it's because it doesn't really understand what the output is going to be, and it doesn't understand what these flags will actually do to the code that's returned. So something that kind of shows that the poor performance on the auxiliary losses corresponds very strongly to poor performance on the actual optimization of the code. So they then do some ablations, which are interesting to look at. So they train the whole thing with so 100% of the data with the auxiliary loss. This is what the improvement over OZ is on the test set. So this is all test set stuff during training. Then if they do 50% of the data, it doesn't do as well. If they do 25% of the data, it doesn't do as well. And if they don't do the auxiliary losses, it also doesn't do as well. So, and this also suggests to me, given the difference between 50% and 100%, given that they only have 1 million functions, I would assume that, because that's a very small data set, I would assume that if they make that 10 million or more, then we're going to see much bigger improvements. So I think this is very interesting, kind of initial piece of research. And I think given it's a small transformer, it's a relatively small transformer with a relatively small amount of data, I do wonder if they're able to collect much more data here, whether this could really push performance even further. And yeah, I mean, what I'm interested in is also not only looking at the optimal LLVM passes, but actually just going straight from the IR to the new IR, which could also kind of bypass the limitations of these combinatorial passes to actually just, you know, create new code that might even not be achievable by combining these kind of fixed set of 120 instructions. Anyway, yeah, so very, very interesting stuff, but obviously the scaling of the data is very evident here. And they do the same just in tabular form. So this is 100%, 50%, 25%, and you see the overall performance at the overall performance at the end. I mean, it does seem to be, although that's quite a big jump, going from 3.9 to 4.9. So you would think the improvements still keep coming, I would think. And then again, so the auxiliary loss, do you include that? If you don't include the auxiliary loss, again, it performs worse than if you do. So, and then they finally do some additional experiments, which is to train the model again with a different aim, which I'll explain in a moment. But I'll pause again. Again, sorry, I know it's not the most structured, not the most structured reading group, but hopefully the main messages are coming through. Any questions at all from anyone? Any comments? Any comments on your side? That Sally, for example, that's one that I know lives and breathes LLVM.
Yeah. So one question I had is, maybe I missed it, but do they mention how many times exactly it gets the syntax wrong? Because one issue that I pretty much think that would be common with an LLM doing LLVM optimization is it gets the syntax wrong just because of how complex it is.
Yeah, so they show that here. So the code compiles 80, it'll be in a number somewhere, but the code compiles like 85% of the time, and it's an exact match only about 60% of the time. So
yeah,
yeah, so they do get the syntax wrong. They also talk quite a lot about how they make, what kind of errors they make, which we could go into a bit in a moment as well. I mean, they talk here, right? There'll be the exact percentage, but yeah, they get it wrong. Yeah, I mean, here they say that 68% of the cases the output IR matches character for character the ground truth generated by the compiler. So let's say then like 32% of the time they get it wrong.
Yeah, that's not bad. I was thinking it'd be worse, but it's pretty good.
Yeah.
And I guess considering they'd increase the sample size, it'd probably even do better.
Yeah. No, I think so. And it's also quite a small transformer. 7B is pretty small, obviously, in the grand scheme of things. Yeah, sorry, I'm putting people on the spot. Any thoughts on your side at all? Jacob at all?
Mainly that, is it, excuse me.
Oh, yeah, sorry, I know you've got a sore throat. Sorry, I didn't mean to put you on the spot with your
okay.
lost voice.
Mainly that it's interesting, like you're saying, the data scaling, how much that would help it. Because I've had a ChatGPT try to generate LLVM code, and it doesn't do a very good job at all.
Yeah.
Which I'm guessing is due to the lack of IR being online, like for web scraping and such. So I think like a well curated data set of LLVM IR or MYR like would really increase the performance a lot over time.
Yeah. No, they mention this actually. They say like it appears that they have not been trained specifically to optimize code. ChatGPT, for instance, will make minor tweaks to programs such as tagging variables to be stored and registered, but it easily gets confused and makes mistakes. They also talk about, I've forgotten where now, but they do talk about this in the training set, that there's not very much LLVM code online. So if you take these like super general train things, then they're not very good at this at all. Here they say it here, look, so compiler IRs do not make up a significant portion of these data sets. And then models like ChatGPT show some promise of understanding. Their ability to reason about IR is far inferior to source languages. So it's much better at Python and things like this. It says here, look, most pro-broken LLMs for code operates on Python. And the data sets available just don't have this kind of stuff, which is why they created their own. Okay, so we'll get to the last section then, which is when they talk about these additional experiments that they do. So they train a new model, and they train the model to take the initial code, take a single optimization flag, and try to predict the new code. So they kind of zone in on this auxiliary loss that was in the original model, but they just try to see how well is that, how well can the model understand the optimization passes. It's almost like, can the model behave as a compiler, I guess is like one way of saying it. Can the model take code and a flag and do the compilation? And if that's the only thing it's trained on, how well does it do? So yeah, so that's what they do. So, well, first of all, we have the ablation of dataset size. We've already seen this. And then they do the ablation of code optimization tasks. So yeah, they train the model to generate not just a pass list, but also optimized code. Oh no, sorry, this is the ablation of that. So sorry, then the one, okay, here we go. So it's the evaluation of single pass translation. So they train the LLMs to orchestrate the optimization passes to produce the best optimized code. They evaluate the ability of the LLMs to emulate the different optimizations themselves. So the input is the unoptimized IR and the name of a single optimization pass, and the output is the IR after applying the pass. So again, like training the LLM to be a single flag, like LLVM compiler. And they generate a new data set for this. Yeah, like using some of the optimization passes from table 1. Yeah, I don't know, that's not too important. They generate a data set. They train a new model from scratch on this pass. And yeah, so figure 7 summarizes some of the results here. So figure 7 is this one, I believe. And they basically order the passes based on how well they're able to be emulated. So the passes towards the left are very hard to emulate, and the ones on the right are easier to emulate. And then they also just include these results for how often these functions appeared in regress. I'm not really sure what the point of this bottom one is, what message you're trying to say here, but they include the percentage of times these passes appeared in regressive versus improving passes in the original results from table 3. So yeah, when you look at table 3 and you had all these kind of regressions and improvements, they just say how regressive or improving were these passes when, you know, in the original data. And so it's able to, I mean, for some of these it really struggles. For some of these it's like, I mean, when you look at, let's look at code compiles, for some of these passes, only 25% of the time can actually generate code that even compiles. So we're not at the point now, particularly with this architecture, that you can just replace LLVM optimization passes with an LLM. It just can't do some of these passes at all. But others, it gets towards 100%. And kind of, I mean, when you look at these, like already through here, we're at kind of 75, 80%. And yeah, this is the exact match code compiles in blue. So they then talk, I mean, they then give lots of examples here of the things that can and can't do. I won't unpack them into too much detail, again, because they're quite low level. But so let's just go through these on a high level though. So a failure due to incomplete information. So there's somewhere literally you can't actually do it because you need the variable name. So they mention on one of these that the path should rename globals, but because the original names aren't actually provided in the data, it needs to hallucinate information. So that's something that's a totally understandable failure. Yeah, Vasalia?
Yep. So would this also be true for like a lot of the hardware flags, which require like information about your hardware memory size, and kind of some of the register information?
Yeah. So so I don't know, but let's just quickly see what they say. So figure 7 summarizes model performance. The average blue score overall passes is 0.84. Exact character match is 73.7% of the time. So I think they improve over the auxiliary results, which is not surprising because it's now a single pass problem instead of multi-pass, and it's like literally what all the model is trained to do. So it's better than it was on the auxiliary, and compilable code 82% of the time. Yeah, so this is what we just saw before. They find no correlation between code quality metrics and its frequency in the generated pass list. So as can be seen, many passes are learned near perfectly, while others prove more challenging. Of the passes that perform poorly, some of them hint at simple improvements to the representation, while others result from deeper limitations of the model's reasoning. So this one I just showed a moment ago is a simple utility pass that renames anonymous global variables using a hash of the module name. Since we do not provide the module name in the prompt, it's forced to hallucinate. So that's obviously understandable. They'll add in future work, they'll solve this. 6b shows an example of the inst combined pass. This is a complex pass that is implemented in over 4,500 lines of C++ code in LLVM. We see that the model correctly identifies the instructions to combine, but makes an error in data flow analysis and substitutes an incorrect value. This is an important optimization that frequently occurs in pass lists that outperform OZ. They will explore an active learning approach in which more examples are provided for complex and difficult passes. So, I mean, they've just said that probably because of the incorrect weighting of hard and easy passes in the training data, it's not able to do the really hard stuff, which you probably need to give more examples for in this kind of active learning approach. They don't mention anything like what you just said. Finally, we present an example of correct model optimization in listing 7, which actually shows something that's impressive. So the example combines several non-trivial code manipulations, which is register allocation, control flow, graph simplification, and instruction combining. They visualize the control and data flow graphs to help interpret the changes that the model made, even on the scale of these small IR functions. There's a sophisticated grasp of the semantics demonstrated, and they think it's remarkable. And I think it is very impressive that it's able to do this kind of stuff compared to more structured approaches. So again, this is the example they talk about here, where again I've not had the time to go into the total details of exactly what all of these passes mean, but a complex set of operations to perform using OZ, basically, which is able to get correctly right off the bat, but still obviously a lot of work to be done, because there's I mean, when you look here, look, there's a decent chunk of these that really are like sub 70% correction, getting it correct. So it's still very far from being a reliable compiler, but very promising, I think. It's an early piece of work. Cool. So then we've only got a few minutes left, so I'll try to make sure we finish on time. I mean, they talk about some related work, some other approaches that are much more structured, some various limitations. So kind of high level, one of the main limitations of LLMs is the limited sequence length. They only target 2K token constant windows. So it's quite small. So they can't apply this for very, very large functions. So if you really want to apply this to very large programs right now, without having a much bigger context window, that's going to be a problem. So that's a general problem, like context window limitations. So compilers perform lots of arithmetic. Whenever possible, expressions are evaluated at compile time to minimize work at runtime and to expose further opportunities for optimization. And the LLMs struggle with this kind of thing. So it's not clear that this is necessarily the correct representation. There are certain kinds of optimization passes that the LLMs have just not done well at. It's not clear whether, and yeah, they say that they think chain of thought approaches could be a better approach to this, rather than expecting everything to happen in a single forward pass. Maybe you could do this kind of incremental step with several different LLMs, perhaps breaking the problem down into subproblems and so on. And also they did mention the active learning. So to be honest, there's also the simple thing of just amplifying the harder examples in the training set more. That's something they haven't done either. So I think there's a lot of things that you can do to try to overcome this. So compilers are fast, and it takes 2 orders of magnitude more time for the model to generate a pass list than it does for the compiler to execute it. So basically having a big LLM does remain an overhead, but still, I'm not sure that's such a big. I think the fact that this is so much better, so much faster than the auto tuning is a strength overall, obviously. It's much faster than the auto tune. It is trained on. It remains an overhead that may prove prohibitive for some applications. Exactly. But I think overall, like being able to get optimal compilations, even if it does require inference through a big model, is definitely interesting. And then the main discussion, so kind of their main concluding points are, so really the first step towards LLMs for code optimization, constructing a model that can predict good optimization strategies for unseen LLVM IR. Again, I think the results are very promising. There's obviously lots of challenges and lots of things where it falls short. And it really is just a pretty simple first kind of stab in the dark at doing this. I think there's all kinds of ways that this can be built upon, including active learning, chain of thought, etc. And what do they say? They hope to inspire the research community to push beyond LLMs for simple max-like code generation into performance-aware code optimization. So I guess my overall thought, sorry, I don't think this is necessarily now the only direction that should be taken when it comes to AI-driven compilation. I think there is a lot of structure that can be leveraged, and tree-based approaches with value functions. There's another paper we'll be doing in a couple of weeks as well that shows really good results from some research done at Google, where they use a graph neural network and a value function to improve XLA passes. I don't think the answer to everything is that we just get a big LLM and ask it in English language to optimize code. But the fact that it does this well is, very interesting. And I think another indication of the general power of LLMs and what just large data and large compute can do. And it kind of, again, adds to the story of just, getting a lot of data, getting a lot of compute can do very good things. And actually, if you have a general enough architecture that's able to learn its own representations without too much inductive bias, then you can do all kinds of tasks, and just reinforcing how task agnostic transform architectures really are is very interesting, I think. And again, as the author said, it surprised themselves as well. Any questions at all?
There's one in the chat.
Okay.
On YouTube.
So I don't actually have it open.
So what are the specific auxiliary learning tasks that the model is trained on during the code optimization process? As I know that the Sapphire used different sets of codes to test the model.
So the auxiliary tasks are just the following. This is it. So this is the prompt, and this is what the answer looks like. So the auxiliary tasks are the inclusion of this sentence to reduce instruction count from 15 to 4. This 15 and 4, these numbers it's trained to predict are auxiliary, as is the code that comes after the colon. So the only thing that's needed at inference is the stuff in bold. That's literally the only thing that it's used at inference. Everything else after this kind of word threading is all auxiliary. And that's it. I don't know if that answers the question. I didn't fully follow the second part of it, but yeah, it's just these points. So the number before, the instruction count before, the instruction count after, and the prediction of the optimized code are the 3 auxiliary learning tasks. Yeah. Any other questions from anyone at all? Any other thoughts or on the kind of what this means for compiler research or anything? I think also, I know we're at time, so to be honest, probably in the interest, we can wrap up soon. But what I would say is, for anybody that does have thoughts, questions, comments, I would very much advise to message in the reading group channel on Discord. I'll be very happy to answer questions and engage in discussion there. There's a few more papers on my radar that are in a similar direction to this. I think there's a lot of really interesting stuff when it comes to AI-driven compilers and where the field might be going. Definitely stay tuned for more. But I guess if there's no more questions, let's wrap up for this week. But thank you very much, everybody, for joining. Really enjoyed going through this with everybody, and I'll see everybody. And we'll start to get these going more regularly again. I know we had a break for a few weeks, but I'm keen to keep going, because there's a lot of amazing papers coming out and a lot to go through. So we'll be here same time next week. And hope everyone has a great rest of the day, rest of the evening, and see everybody again soon. Thanks a lot, everybody. Bye for now.
Thank you. Bye.